We now continue in Chapter 1 with Section 1.2, Exponential Growth with Stocking or Harvesting. We're going to try to change up the model that we've been working with a little bit. Instead of just assuming constant percentage growth or percentage decline, we're going to look at this idea of stocking or harvesting. So, defining those terms. So stocking and harvesting are basically the same thing, just with a different sign attached to it. Stocking just to add a constant amount, and harvesting to subtract a constant amount. Notice these are not percentages. So let's just jump into it with this sand crane population example in the book. So I'm looking at examples 22 and 24 in the book about the sandhill crane population. What they say is that it decreases by a constant 6% each year. So if we were to draw a picture of that, remember we can draw our flow diagram with P of t on the inside of the diagram and an outgoing arrow of 6% each year leaving. So remember we take P of t minus 1 to represent the previous year's population in how it's changing. But now with this idea of stocking, researchers are trying to stem the idea from the population going extinct, trying to help them in at least staying stable. So they're adding 9 cranes to the population each year. So that would represent just a constant 9 going into the bubble. So this is the only information they gave us in terms of change to the population. So that is our complete flow diagram. So with the cleaned up version of our flow diagram, this allows us to make our DDS, our discrete dynamical system equation. So, as usual, we start with P of t on one side. And the right side, again, always start with P of t minus 1 for the current population. And make the changes. So we know from incoming, there's a plus 9 occurring, so we just add 9. No P of t minus 1 attached to that because it doesn't depend on the current population size. And subtract 6% or 0.06 P of t minus 1. And this is the equation that we can take to Excel to really see what's going on and if this is an effective thing that the researchers are doing to help the population out. So, just like previous videos, we have our Excel spreadsheet set up with an example of what the equations we're looking at, and notice I've written it without the stocking yet. So this is just if the population were just decreasing at 6%. And we're going to assume, which I believe the book is doing, a starting population of 50 sandhill cranes. So, writing our equation in, we take the previous year's population, subtract our decrease rate, and remember to hit F4 to make that a fixed reference cell, multiplied by the previous year's population. And then I can drag that down and see what the population would be after a certain amount of time. Now why I'm doing it this way is, first, before the stocking, we can predict if the population keeps decreasing at 6% per year, when will the population decrease to nothing or become extinct? So I dragged the population equation down for a long time just to see what we get. And a key thing that the book notes is that the population technically in this model will never reach 0. With a constant percentage decrease, 0 is actually known as an asymptote. We get really close to it, but we don't actually reach the value. So your book just estimates that, well, getting below a population of 1 is enough. That's basically the idea of a population being 0 in this model. So we see it happening around this row right here. So the question is, what year is that? So we go back up and make sure that we redo our time and just drag that down to that certain point. And I'll just drag it down to the very bottom, but we look at which row that occurred in, and it looks around 63 or 64 years is how long it will take the population to decrease down to 0. So what about this idea of stocking? Adding an artificial amount of cranes to the population each year to see if we can make the population not decrease to 0. Keep it from going extinct. Well, then all we have to do is change our model just a little bit in the equation. So I go back to the formula, and I highlight up here, and this is the first cell after the initial population. Well, the only thing we need to do is just add our 9. And I again made it an absolute cell reference over here because maybe we'll change the stocking number in the future. So I should make sure that that is an absolute cell reference when we make that occur. And when I hit enter, now I see that, well, the population did go up by 6 in that first year. Now we should look at the rest of these formulas and note, if we can see in the formula bar, changing between these two, I only changed one formula cell. So if I want this to apply to the rest of the cells, I really should re-drag this to recalculate all these values. And we see now that, yes, the population is actually increasing. It's going up. We could play around with these values to find out maybe if there was a equalizing sweet spot. Maybe the population keeps at a steady, constant population with just the right amount of stocking or just the right amount of decrease rate. But this is a question we might ask in future sections.